Hello, Algebra 3 students. Today we're going to talk about triangle inequalities and the triangle inequality postulate. This says simply that in a triangle, any two sides added together are going to be greater in length and value than the third side. So all that is something that you just need to know about for the sake of a proof as we do proofs later on. And what that looks like is this. You'll have a square plus, or actually not a square, but a plus b is going to be greater than c, and a plus c is going to be greater than b, and b plus c is going to be greater than a. And that is all the triangle inequality postulate says, is that when you add two of the sides together, it's going to be greater than the third. Any two added together is greater than the one remaining. Fairly self-explanatory, but you are going to want to make a note of that because when you go to write proofs, that may be something that you need to refer to. And when we do the proofs, one of the things that we do is we will quote the name of the postulate. We don't have to write the entire postulate or give an example of it. We just refer to it by its name. And then that tells us your logic for why you went in a certain direction with your proof. Okay, so that is something that you will need to write down in your notebook and refer back to later. And I would even put out here to the side, proof work, because that's going to be something that you're going to use to do proofs. Okay? So let's talk about the Pythagorean inequalities. So far we've been using the Pythagorean Theorem just to help us find the missing legs or lengths of the hypotenuse in a right triangle. And we know that that formula looks like this: a squared plus b squared equals c squared. We know that this is related to a right triangle, something that looks like that, right? Well, I take that back. That's a right angle, not a right triangle, but it looks like this. The right triangle looks like that. It has a little square in the bottom. Okay, so what we can do with this, however, is we can use it to evaluate when we have all the lengths of the legs of a triangle. It can actually tell us whether or not that triangle is obtuse or acute instead of right. And the way we do that is with inequalities. A squared plus b squared, that is greater than c squared, is going to be an acute triangle. So it's going to be, think isosceles or regular triangle. A squared plus b squared, that is less than, or a squared plus b squared, that is less than c squared, is going to be an obtuse triangle. So one that looks like that, right, in some form or fashion. All right, so that is something that you're going to want to also put in your notes and keep, because you are going to have problems that ask you, given these three sides, what type of triangle is this? And so, in fact, we're going to do one now. We're going to do 3.1. And 3.1 says, the lengths of the sides of a triangle are 7, 5, and 4. Is this triangle a right triangle, an acute triangle, or an obtuse triangle? So which one of those is it? So what we're going to do is first determine which one goes in the C. We know from this formula that C is always the hypotenuse. We also know from working with right triangles that the hypotenuse is always the longest side of the right triangle. So if this is a right triangle, then 7 has to be C. And 5 and 4 could be A and B. It doesn't matter because they're combined. So we'll just call this A and we'll call this B. So what we're going to do is we're going to evaluate what these two give us. So we're going to say A is 5 squared and B is 4 squared and C is 7 squared. 25 plus 16 is 41 and 49 is the result of 7 squared. Well, 49 is greater than 41, so that would make this an obtuse triangle. And that's all you have to do. That's all there is to figuring it out. You compare the legs and the hypotenuse, and then you put in the proper inequality sign, and then that inequality sign tells you which one of these it is. So that one's pretty straightforward and easy to do. So, do we remember what polygons are? Polygons are simple, meaning they don't cross, the sides don't cross each other. So simple, closed, straight side objects. My dog is barking up a storm. I don't know what he's doing. Or straight-sided shapes. What that means is a circle is not a polygon. A shape like this is not a polygon. A shape like this is not a polygon. Let's see, a shape like this, not a polygon. So what is a polygon? A square is a polygon, right? A triangle is a polygon. Some wackadoo shape that has straight sides all the way around, that is a polygon. And you can even have polygons that do this. That's a polygon. So it doesn't have to be all external angles. You could have some internal angles as well. Or what I mean by that is concave angles. And a concave angle on a polygon is one where you can start drawing a straight line from the interior of the shape to the other side, the interior of the shape, and you cross two of the sides. Two or more of the sides, actually. So if you can do that on a shape, that's what we call concave. Basically, the shape just makes a little cave that you could, reach into. Like this right here. That's concave. Because you can draw across the borders. This one, however, this triangle, no matter what you do, you go from corner to corner even, you're still on the inside of the shape. So this is what we call a convex shape. A convex shape is where you can't cross the external border of the shape by drawing from inside to inside at any point. Right? So that's the two differences between polygons. They're either going to be concave or they're going to be convex. And most of what we deal with is convex. But I know you remember shapes that we've done to find perimeter, like these types of shapes. That's a concave shape because we can draw a line across the outside and hit the outside of the shape. So that'd be a concave shape as well. Right? Okay, moving on. Let's talk about similar triangles and how we can find missing information. I think actually the best way to do this is just to jump into one of the example problems. Let's do 3.2. Let me pause and I'll draw it for us. All right, here's example problem 3.2. We have two similar triangles here, and we can see by these angles in the center that we have some vertical angles. So we know that these vertical angles are congruent. So I've put a tick mark in each one to show that they're the same. And we're also told that these two angles are congruent. So if we have two angles that are the same, we know that the remaining angles have to be congruent as well because of the nature of the triangle and how it is constructed. If whatever this is, this can only be one thing left over because it has to equal 180 degrees in the center. So if this is A and this is B, C is left. If this is A and this is B, or I'm sorry, if this is A and this is B, then C is left. And C's are going to be the same. All right, as long as these two are congruent, we know that that third one is congruent. So one of the ways that we can solve, in fact, we'll solve both ways. You can solve this by using either the scale factor method or the ratio method. And I think we're just going to go ahead and solve both ways so you can see that it doesn't matter which method you use. What matters is the one that you're the most comfortable with. And also, sometimes looking at the triangle itself will dictate which way is better for you to use. So with this one, it's not going to be so hard because we just have one unknown on each triangle. But in other problems where you have more than two unknowns or more than one unknown on each triangle, you might want to use one method or the other, depending on where those unknowns are located. So let's set up this scale factor method. So I'm going to label these triangles. I'm going to label this triangle A and triangle B. And I'm going to give these points, these angles, each a name for the sake of orientation. So I'm going to call this one in the middle, let's call that C. And then angle 3 is going to be D. And this is going to be E. All right, so angle 3 is D, and then angle 2 is E. And I'm counting the tick marks when I say angle 2 and angle 3. So now I have some reference points to where I can tell which sides are the same, right? CD, CD. And I did that on purpose, the same letters, so that I can tell my congruencies a lot easier. You know, technically, in similar triangles or in a figure, you wouldn't name 2 points the same thing because it could be confusing. But when you have a similar triangle, it could actually make it a little bit easier to figure out which sides correspond to which sides. So that's the way I like to do it. You can do it whatever way works for you. Okay? All right, so I'm going to look at these. Let's see. So CE here and CE here. We have the values for CE and CE. So those two sides correspond. So I am going to set them with a scale factor equal to each other. 5 times some number scaled up gives me 7. So 5 times some scale factor is going to equal 7. So what I'll do is I'll divide both sides by 5. My scale factor is going to equal 7 divided by 5. That's my scale factor. And so I did A times the scale factor equals B. That is the formula that I'm going to use to solve all of my missing information, all of my missing numbers, right? I'm going to take the number from A, the value from A, the scale factor that we discovered, and put in the value for B. Whether it's an unknown or a known doesn't matter. All right, so let's start with our first unknown, CD. We don't know what CD is on triangle A. So on triangle A, that's X. So that's going to be X times the scale factor, 7 over 5, equals CD on triangle B is going to be 6. So what do we do to get rid of a fraction times a variable? We multiply times the reciprocal, right? So we're going to do the same thing on this side. We put this over 1, And these cancel, so I'm left with x is equal to 30 over 7. All right, so let's do the same thing for y. So y is DE on triangle B, and 4 is DE on triangle A. So for A here, I've got 4 times a scale factor of 7 over 5 is equal to DE, which is y. All right, so 4 times 7 is 28 over 5 is the value of y. Easy peasy. That's all we had to do. And that's why I put the same points at each angle, just so I can keep it straight, which side is which side. All right? So let's do it with the proportion method. So the proportion method, I do the same exact thing. I just make sure that I have all of triangle A and all of triangle B on the same side of the fraction. So for instance, I'm going to do CE, the side CE, right? That is going to be 5 over 7. All right, and now if I do CD, line segment CD, that's going to be x over 6. And if I do line segment DE, then that is going to be 4 over y. So all I have to do is set this up as a proportion for each one of these and solve for the unknown element. So 5 over 7 equals x over 6. That's going to be 30 equal to 7x. So divide both sides by 7. 30 over 7 is equal to x. I got x is equal to 30 over 7. So those match. Now if I do the same thing for my DE, I get 4 over y. 5y is equal to 28. Divide both sides by 5. Y is equal to 28 over 5. 28 over 5. 28 over 5. Same value, just both of them in different ways. So it depends on how the triangle is set up, how you see it, what makes the most sense to you, right? And then that's the method you use. So let's try another one. All right, in example 3.3, all we're told is that we have right angles here. But we have vertical angles, so we know that they are congruent. And if these two are congruent, and then I have these angles here that are congruent, then that means that these angles here are also congruent. That also means that these lines have to be parallel because these are alternate interior angles, and that's the definition of parallel lines, creates those alternate interior angles that are the same. All right, so now I'm going to do the same thing I did before. I'm going to use a different color this time, though, to make it stand out a little bit better. This is A, and this is B. I'm going to call this C, and then 1 and the right angle, I'm going to call that D. Right angle is D, and then angle 2, I'm going to call it E, and I'm going to call this E. All right, so now I have CD, DE, and CE as my sides on the two triangles. So now I need to find out or figure out how to find the scale factor. So I'm going to say A times the scale factor is equal to B. That's what I'm going to use. So let me take CE. I'm going to do CE first. So I'm going to say 7 from A, 7 times some scale factor is equal to B. CE is 10 on B. I don't know if you can hear him or not. My dog is chewing on something, and he's really trying to eat it, I guess, and tear it up. But it's really loud and annoying. Stop, Roscoe. So 7 times some scale factor is 10. So if I divide both sides by 7, my scale factor is going to be 10 over 7. If I do it that way. So now I can use this to solve for the rest of them. So again, I'm going to use A times the scale factor equals B. So A is Y. So Y, and this is for CD, Y times the scale factor of 10 over 7 is equal to 8. Because here's 8 on the other one, on B. So we multiply times the reciprocal on both sides. And I get Y is equal to, oh goodness, 56 over 10. Y is equal to 5.6. I just went ahead and divided for the sake of dividing. When you have it divisible by 10, it's pretty easy to just go ahead and do that. So let's do DE now. DE, I'm going to do the same format. A, which is, oh goodness, I can't do A and B like that because A and DE on A is X and DE on B is Z. I can't do it at all. But I can use Pythagorean Theorem to find Z because I have two values here. So let's do that. So I know that my legs are 8 squared plus Z squared and the hypotenuse is 10 squared. So 8 squared is 64 plus Z squared, and that equals 100. Z squared is equal to 36. So when I unsquare both of those, Z is equal to 6. So now I can actually do DE because this equals 6. So now I can say A, which is X times the scale factor of 10 over 7, is equal to 6. So I'm going to use the reciprocal. And that is going to be X is equal to 42 divided by 10. X is equal to 4.2. Easy peasy. Now we could have just as easily done this with the ratio approach. And if we did, we would still have had to solve using Pythagorean's theorem to find this unknown here. So let's do it that way and see how that works. So I'm going to have A over B, and then I'm going to do line CE, line CD, and line DE. And I'm going to use what I know, what I've been given. So for CE, A is 7 and B is 10. CD, A is Y and B is 8. For DE, A is X and Z is 6. And if we had not solved for Z, we would put a Z here, and we wouldn't have been able to do this. We would have still had to solve with Pythagorean's theorem to find out that Z is 6 in order to solve. Now all we have to do is say 7 over 10 is equal to Y over 8, and 7 over 10 is equal to X over 6, and then we multiply, we get 56 over, we get 56 is equal to 10Y, and then we divide by 10, and we get 5.6 is equal to Y, which is the same thing we had here. And 7 times 6 is 42 is equal to 10x. We divide by both sides by 10. 4.2 is equal to x. And I don't know why it does that sometimes. It's thinking. It doesn't want to do it. Anyway, 4.2 is the answer. I'm going to write it better so you can see it. I'll rewrite it. Sometimes it glitches on me. That's okay. I can just redo it. 4.2 is the value of x, and it's the same thing we got over here. So you can see either method works. It's just about sorting it out and putting it in the right spot. So either way, we would have had to do Pythagorean's theorem to figure out what one of those sides were so we could have some type of a reference. Because you cannot solve a proportion statement when you have two unknowns. Just like we couldn't solve this having two unknowns either. All right. So let's look at 3.4. All right, here we have example 3.4, and we have one small triangle within the other triangle, and we see that both of these are 90-degree angles, and because these are triangles within a triangle, the angle at the front here to the left is going to be the same because it is the exact same angle for both triangles. Now I will say that sometimes this is confusing to have them on top of each other like that. So what I like to do is draw them separate from one another. Give myself, help myself think straight. So I redraw. This is A. And by definition, we know that this one is going to be congruent to this one because this angle is the same. These two angles are the same. So these two have to be the same. All right, and this is 6 and this is 4. So the other angle, I'm going to draw it or triangle, sorry. I'm going to draw it a little bit bigger. All right, there is now 6 plus 4. This is going to be 10. This is the same as that one, and this is the same as that one. And this is going to be A plus B. It's both of these put together, A plus B. And then this is C. Now, because these are both drawn with the same base and the same angles in the same location, I don't really need a point of reference for it. It's pretty straightforward. I don't need to give myself extra letters to keep up with because I can visually see the sides line up, right? That makes it a little bit easier. So let's go ahead with the way that we know we need to do this. So we have a missing A here, and that's the hypotenuse of this triangle. So we can easily find A. We're just going to do 6 squared plus 4 squared is equal to A squared. That's 36 plus 16 is equal to A squared. And that's going to be 52 is equal to A squared. We unsquare both of those, and we find that 4 times, is it 13? Yeah, 4 times 13, so 2 times the square root of 13 is the value of A. So I can rewrite that. I can take A out, and I can put 2 times the square root of 13 right here, and I can put 2 times the square root of 13 here. Sorry, I am fixing to get him out of here. He's making too much racket. All right, now I can do a scale factor analysis. Given that I have 2 different bases, I can figure that out. I'm going to again label this, but I'm not going to use A and B because I already have a B here and I don't want to confuse myself. So I'm just going to call this triangle 1 and triangle 2 and make that, actually I'm not going to do that either because I don't like using numbers. Let's call this X and Y. Those are far enough away that I'm not going to mess those up. Okay, so here's what I'm going to do for my scale factor. Since I have 6 and 10, I'm going to say X times some scale factor, triangle X times some scale factor, leads me to triangle Y. So 6 times some scale factor is going to lead me to 10. Divide both sides by 6. My scale factor becomes 10 over 6, which reduces to 5 over 3. Right? So we have that now. Now I can use this same formula to do the rest of them. So I'm going to find C using this. So 4 times my scale factor of 5 over 3 is the value of C. So that's going to be 20 over 3 is equal to c. So now I know what c is. And that is 20 over 3. Very straightforward there. All right, so now I can find the value here either by using Pythagorean's theorem or by using the scale factor. And I think what I'm going to do is use the scale factor just to be to keep it continuous. I am going to move this out of my way though. I'm going to put it right up over here. This is where we found the value of that. So let me continue to use the scale factor for the hypotenuse. So this time the hypotenuse of x is going to be 2 times the square root of 13 times 5 over 3 is equal to 2 times the square root of 13 plus b. And this works because I have only one unknown, and that is my value b. So I am going to multiply by the inverse operation here. So 3 times 5, or 3 over 5 times this, is going to cancel that out, and I'm going to say all of this over 1 times 3 over 5. And this is going to be 2 times the square root of 13 is equal to 6 times the square root of 13 plus 3b all over 5. Okay? And what I can do is I can actually split this up. You want to split this up into 2 separate parts so that you can move it around. So I'm going to put both sides over 5. And I'm going to subtract this from both sides. I think. Yes, minus 6 times the square root of 13 over 5 minus 6 times the square root of 13 over 5. So what I've got to do now is I've got to convert this. So what I need to do is say 2 times this. So I'll have 10 times the square root of 13 over 5. So 10, because 2 times 5 is 10, that gives me 2 whole. 10 minus 6 leaves 4 times the square root of 13 over 5 equal to 3b. Sorry, that's supposed to be b, over 5. Now, we know that with equations, if they are both over the same denominator, what can we do? We can get rid of the denominator. So that means that I have 4 times the square root of 13 is equal to 3b. So all I have to do is divide both sides by 3 and say that 4 times the square root of 13 over 3 is equal to b. And that is the value that we have for b. And that's correct. 4 times the square root of 13 over 3. Now I want to put these together. I want to add them up. So I'm going to say 2 times 3, that's 6 times the square root of 13 over 3, because that'd be a whole number 2, plus 4 times the square root of 13 over 3 is equal to 10 times the square root of 13 over 3. And that is the value here for this side. 10 times the square root of 13 over 3. That is the length there. Okay, so you've seen me do all of this. I'm kind of running out of room. So I'm going to do the ratio version now, right? I'm erasing all of this. So if you didn't get that all down, you need to rewind and pause. And let's do the proportion method now. So the proportion method, I'm going to have triangle x over triangle y, and I am going to use the A, we'll call that the base leg. That's going to be 6 over 10. B is going to be the upright leg, and that is going to be 4 over, oh, and what was that? That was C, right? Yes, that was C. And then, let me put C here, and this was A plus B, and this was A, just so I have that straight. All right, and so now I have the hypotenuse, which is C, and that was A over A plus B. All right, so I can find C by doing this right here, right? So 6 over 10 equals 4 over C. 6C is equal to 40. C is equal to 40 divided by 6, which is 20 over 3. Check. We got that right. And that does not look like a check. It looks like something wonky. So check. We got C correct. Easy peasy. All right, I'm going to move this over out of the way. I tend to write in the middle and end up having to move stuff out of the way. So the only way that we can find A was Pythagorean's theorem. That, you know, regardless, we had to find a value on this side in order to compare it to a value on this side. Well, now that we have A, which was the easiest one to find, we can actually replace this with the square root of 2 times the square root of 13 right there. So now we can take this proportion and compare it to this one. And because A is the same thing here, we want to do that here. 2 times the square root of 13 as well, right? So we can say 6 over 10 is equal to 2 times the square root of 13 over 2 times the square root of 13 plus B. And I know what you're thinking. You're thinking, this is not going to be the same answer. It is, trust me. So we have 10 times 2, that's going to be 20 times the square root of 13 is equal to 6 times 2, that's 12 times the square root of 13 plus 6b, right? If I subtract 12 times the square root of 13 from both sides, that leaves me 8, right? So I'm going to write that over here. Actually, I'm just going to roll up. I think I have some room. Yes, I'll do that. So 8 times the square root of 13 is equal to 6b. If I divide both sides by 6, and then I reduce, I can divide this by 2 and divide this by 2, and I get 4 times the square root of 13 over 3 is equal to b. And that is exactly the same thing that we found here. But if that is the value of b, you still have to add it the same way we did before. You still have to say 4 times the square root of 13 over 3, 2 times the square root of 13 plus that, right? That's the side. So we said 2 times 3 would be 6 over 3, because 6 divided by 3 is 2. 6 plus 4, that equals 10 times the square root of 13 over 3. And that is what we found here. So this checks that. We always had to solve that with Pythagorean's theorem. We didn't have a way around it, and that checks. And so you can see, even on your more complicated ones, it still works. Either proportion or scale factor, it does not matter. You're going to get the same answer if you do the math correctly. So we have one more. It's kind of a doozy, and we'll go through it and then we'll be done. All right, this figure is unique and famous because it contains 3 similar triangles. So if you can't see them, you have a right triangle up here with the angles M and K. All right, so you have a right triangle here with the angle M. So by default, this has to be K. Same thing here. In this triangle, you have a right triangle or right angle with K. So by default, this has to be the measure of M. So what I would like to do to kind of make this a little bit easier on the brain is to draw these separated. So I'm going to do that now. This is the big one, and this is M, and this is K, and 4 plus 8 is 12. This is angle A, and this is angle, or line segment A and line segment B. And what I'm going to do is I'm going to give this right triangle here L, all right, for lack of anything a better name, because L is in itself a right angle, so it's very fitting. So my right angle is going to be called L, and that's going to help me know which sides are which, right? Because the angles are the ones that determine the ones that are similar, which sides are similar. So now I'm going to draw the smaller one. And again, this is not to scale. My right triangle is L, and then I had M down here, and I had K up here. And then my other triangle is here. Here's my right triangle. This is L, and this was K, and by default, this one would be M. So now I'm able to see my congruent sides, right? That makes it a whole lot easier to tell what I have. So now I just need to put in my dimensions. So this is A, this is 4, this is 8, this is B, and we're going to call this H for height for just now, right? So that helps us with that. Those are the same side because they were the same line down the middle. So they have the same value. Now, however, I can see all the sides and I can draw a relationship because I've labeled everything. So now I know what is what, right? Which helps because this is actually, it's a similar triangle, but it's actually a mirror image, right, to this one. This one and this one are facing the same direction, almost, but it's flipped. So it's kind of, you know, that's why I like to put the letters on here so I can see what is what and make heads or tails out of it. All right, so first let's do this triangle and this triangle. So we'll call this the big triangle and the little triangle and the medium triangle, right? So that'll help me. So I'm just going to write big, little, and medium, so I can tell the difference between these, because I've got too many letters running around. It's driving me nuts. All right, so in order to draw conclusions, let's do some scale factoring first for the big and the little. So I've got the big one on top, or actually no, I'm sorry, the big triangle the little triangle times some scale factor is equal to the big triangle. Okay? And I did that because I know 3 times 4 is 12. So I know what my scale factor is going to be already for this one. So the little triangle, we're going to do LM. Oh, so that's not going to work either, see? LM would be A. So let's just do that. So let's do LM. And the little triangle, that's 4 times some scale factor, is equal to A. So that really doesn't help me because I have 2 unknowns. I can't do that one. So what I need to do is I need to do 2 that have a known value. And I can't use scale factor to do it. So what am I going to do? This is a situation in which the proportion is going to make more sense to use. And I'll show you why. All right, so let's just do the big one and the little one. All right, so if I have LM, and I've got the big one and the little one, right? And I have LM, the big one, that's A, and the little one, that is, LM is 4. All right, and if I have, let's see, LK, on the big one, that's B, and on the little one, LK is H. And then I only have one left, and that's MK. And on the big one, MK is 12. And on the little one, MK is A. All right, when you have 2 unknowns, and it doesn't matter which 2 of these we put together, you're going to have 2 unknowns. If the 2 unknowns are the same base, they're the same variable, then you can still work with that. So I'm going to use LM and MK, and I'm going to set it up so big one over the little one. I have A over 4 is equal to 12 over A. Do you see where I'm going? A times A is A squared. 4 times 12 is 48. A squared equals 48. I can unsquare that. And I can say that A is equal to, let's see, 2 times 24. So 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. So it's 2 times 2. That's 4 times the square root of 3. So that's what the value of A is. So I can go up here and I can say in all of these that A is 4 times the square root of 3. So now I have A done. And I might as well put it in the original as well. And I'm going to put H here too, because we're going to have to find him as well. All right, so there's that. Now up here, I can also substitute it into my setup here. 4 times the square root of 3 and 4 times the square root of 3. All right, that still doesn't help me with these 2 in the middle. Right, if I were to multiply this one times this, I'd still have 2 unknowns. This one times this, I'd still have 2 unknowns. This is where you need to do the Pythagorean Theorem, when you've got to figure out one of these unknowns. So that's what we're going to do. Let's just use the big one. And since 12 is the hypotenuse, we're going to say 4 times the square root of 3 squared plus b squared equals 12 squared, right? So that's going to be 16 times 3. That is going to be 248, possibly. Let's see. 16 times 3, 18, carry 1. No, this is 48, sorry. 48. My brain is not necessarily working on all cylinders today. So 48 plus b squared is equal to 144. Subtract 48. My pen isn't working on all cylinders either. from both sides. B squared is going to be equal to 96. Square both of those. And B is equal to 4 times the square root of 6. All right, so now we know what B is. So we can take this out. 4 times the square root of 6. 4 times the square root of 6. 4 times the square root, of 6. So now we have options. We can either put 4 times the square root of 6 right here, and we can do a proportion, or we can just use Pythagorean's theorem and find h either way. So let's just use Pythagorean's theorem for this one. All right, so 4 squared plus h squared is equal to 4 times the square root of 3. And the reason I said that is because we already know what this is. This is 48. We've already done that over here. So 16 plus h squared is equal to 48. Come on. My pen is not working. Well, that stinks. Let's see if this works. Nope. I think it's the program. I think it's decided to slow down. So let me pause. It's my whole computer. It's not doing anything. Okay, well, I've got to wait for it to catch up. 48. This kind of stinks to get to the very last problem, the very last little bit, and then your computer wants to die. Let's not do that, computer. Let me see if I can do anything on here. Can I bring my calculator up? Nope. Well, there it goes. That comes back. Let's see if this will work now. Nope, it still is not working. Let me move this piece of paper and see if that makes any difference. That's not making any difference either. I think it must be good notes. All right, so let's walk through this. Just pretend with me, all right? 16 plus h squared equals 48. H squared is going to equal 48 minus 16, which is going to be 32. If we unsquared h squared and we unsquare 32, we're going to find that h is equal to 4 times the square root of 2. So that would be the height here, 4 times the square root of 2. And that's really all I have for lesson 3. It's just a whole bunch of similar triangles and all the different ways to work them. And I wanted you to see a opportunity or a problem in which one method is better than the other. And it really, like I said, it depends upon the triangles. So what you've got to do is, if you don't know, right? You're like, I'm not sure which one is the best method for this. Try both of them, right? Try one, and if you start going off the rails and say, you know what, this is not working, I don't have enough information, let me do it the other way, and do it the other way. And don't forget about Pythagorean's theorem, because you're going to need to use that in order to solve some of these right triangle problems. All right, and that's all I have for lesson 3. I will see you in, I was going to see if it was writing. Nope. I'll see you in lesson 4. Let's see if I can get this to actually respond and write something. And I'm going to use my mouse to see if it'll, oh, there it goes. My mouse is writing. So my pen has just quit for some unknown reason. So that's supposed to be 48. And again, h squared equals, you see why I use my pen is so much better than this stinking mouse. H is equal to 4 times the square root of 2. And we would put that in here and here and here. All right, I will see you in lesson 4.